In an inductive proof, we need to be 100% rigorous. It's not enough to simply accept a conclusion just because it feels intuitive. Instead, each reasoning step must be painstakingly validated. We must show that it follows from prior ideas that we have proven from observation. It's not enough to show that you're reasoning from some assumption that seems plausible. Now, many of you probably think that proving our modern multiplication method will be easy because it is so intuitive. This method is especially intuitive if you already understand our place value number system really well. However, intuition is not enough in induction. We must demand from ourselves a completely airtight proof. Before watching today's video, you may want to try proving the modern multiplication algorithm to yourself real quick, using only ideas that we've established so far in the series. Then I challenge you to compare your steps to mine, and I think you'll be surprised how hard it is to actually gain certainty on the method that we all accept today. You may even disagree with the steps that I take in this video. You'll probably say that a lot of them are unnecessary. If you do, tell me in the comments. I'm especially interested if you disagree with my way of proving this, and especially if you think some of these steps were not needed. So let's give an inductive proof of our modern multiplication algorithm here on Inductica. Motivation 1. We're going to return to our young hero, Algamesh, as he continues figuring out how to do the different operations with his new number system. Recall that in previous videos, Algamesh invented a new number system, a number system which was superior to Roman numerals in that it could display information much more efficiently. However, for this number system to be any good, Algamesh needs to show that he can do all 4 operations with this number system, and today he's going to try and figure out a method of multiplication. This, of course, leads Algamesh to the following question. Question 1. How can multiplication be done reliably, easily, and quickly with my new number system? Investigation 1. Algamesh is going to start with something really simple. He's just going to multiply 2 numbers. 7 times 6. He's going to repeat 6 7 times, and of course he's going to use the method of addition to do this, and that comes from a prior video which I've cited in the description. He adds all these up. I'm not going to go through how he does that so as to not bore you to death, and that comes out to 42. Next, he's going to try something more challenging. 7 times 25. Now, he knows from Roman numeral multiplication that he can multiply this number by the different parts of the second number. He can multiply the 7 by 5, and he can multiply 7 by 20. This comes from the same reasoning that was done in a prior video, Roman numeral multiplication. So I've included that link in the description as well as a prior induction. First, he's going to repeat 7 5 times, and then he's going to repeat 20 7 times. And then he's going to add these 2. Okay, so he's split this problem into 2 easier problems. So 7 times 5, he already knows how to do that. He adds 5 to itself 7 times, and that's 35. So that takes a long time, but he knows how to do it. And he figures he's going to be able to come up with some way to make this quicker in the future, so he's not too worried about it. Next, 7 times 20. Again, this is doable through repeated adding. He's just adding 20 to itself 7 times, which comes out to 140. You could probably do this one in your head because you're using certain tricks that you've learned. But remember that Algamesh has not learned those tricks. He is the fictional inventor of these tricks. So make sure that you take Algamesh's point of view as you go through this process of reasoning with me so that you don't assume anything and so that you can follow proper inductive logic. So next, he's going to find the total by simply adding these to one another. 140 plus 35. And what's that going to give him? Again, I'm not going to show you the steps, but there are steps Algamesh would have had to do, and that gives him 175. Next, he's going to challenge himself even further by multiplying 2 two-digit numbers. So it's going to be 35 times 43. Okay, so once again, he's going to break this multiplication into parts. He's going to do 5 times 3. Adding that all up, once again, comes out to 15. Next, he's going to do 5 times 40. Once again, this is actually pretty doable just by adding the numbers up. So he's going to add 40 to itself 5 times. Once again, kind of a pain, but he's able to do it. He's just getting the feel for this to see where he can kind of shorten the process. And of course, he's going to find ways to shorten the process. Okay, so we're done with this one. The 5 has been multiplied by every part of the second number. Once again, using that same idea from Roman numerals, how we multiply each part of the first number by each part of the second number. And we're done with the 5. Now we do 30 times 3. Notice how this is a 3 here, but it's really a 3 in the tens place, so it's 30. 30 times 3. So is he going to repeat 3 30 times? No. He's going to use the commutative property of multiplication to reverse it. And now he's just got to add 30 to itself 3 times, which is easy. 90, okay? Well, it's easy for me. I'm doing it in my head, but Algamesh can do it on paper easily, but with some consumption of time. Finally, Algamesh is going to have to do 30 times 40. Okay, this is where it's going to get a little gnarly, maybe. So 30 times 40. Adding 40 to itself 30 times is just unacceptable. At this point, Algamesh says, okay, I'm going to have to come up with some faster way of doing this. So Algamesh has an idea after pondering this for a while. He writes it out in Roman numerals. So how would this work out in Roman numerals? Now, this, of course, would be 12 C's. Okay, why do I say of course? Well, each of these gets multiplied with each of these. An x times an x produces a c. 3 x's over here and 4 x's over here. So he knows he's going to get a c for each pairing, and there are 3 times 4 pairings. 3 times 4, he adds that up, gets 12, so he knows he gets 12 c's. Written out in his numeral system is 12 hundreds, okay? So this is 10 and 2 hundreds. 10 hundreds is 1,000. He knows that because of the place value system, and 2 hundreds is 200. 1,200. These underlined numbers are what I'm going to call, or what Algamesh will call, the subproducts. These are the products of each little bit of the first number times each little bit of the second number. At the end, Algamesh is going to add all of these up, and that's going to give him his overall result. And sparing you the time, of course, adding all of this stuff together gives us 1,405. Now, Algamesh is not happy with this as some kind of repeatable procedure that gets the answer quickly. So he's going to try another one to see if he can kind of work his way towards that. Next, he's going to challenge himself with the problem 56 times 37. Another 2-digit number. Since 2 digits he's kind of seeing is the point at which he starts having trouble consistently doing. 6 times 7. Once again, worth noting that he's adding these still. He doesn't have multiplication tables yet because he doesn't exactly have reason to think yet that the multiplication tables will be able to consistently help him. So he's still adding for now. He knows he's going to have to do something like that eventually. But for now, once again, he's adding. So imagine him adding 7 to itself 6 times in a laborious, awful process that I'm saving you from. Okay, next it's 6 times 30. How is he going to think about this? The first thing he's going to think about in order to figure this out, he's going to think about a 1 times an x. A 1 times an x is an x. And he's got 6 ones here, 3 tens here. Now, since 1 times x is x, he knows he can do 6 times 3, and that's going to tell him how many tens he has. Since this means 3 tens, he's just going to do 6 times 3, and then that will tell him how many tens he has at the end. 6 times 3 is easy. That's 18. 18 is 10 and 8. So first he has to think about 10 sets of 10. That's 100. And then 8 sets of 10. That's 80. So 180. Okay, so that's his second subproduct, and I should underline the earlier subproduct. Next, Algamesh has got to do 50 times 7. Now, of course, he's going to change that around by doing 7 times 50 using the commutative property of multiplication. And he's going to do the same thing as last time, 5 times 7, and then that's 35 tens. By adding 30 to itself 10 times, he knows that's 300, and then 5 tens is 50, 350. Okay, that subproduct is done. Next, he's got to do 50 times 30. So he knows that this is going to be a certain amount of tens multiplied by a certain amount of another amount of tens. And each of these is going to produce 100. He knows that from Roman multiplication. He knows that it's going to be 3 times 5, which he adds up to be 15. And that's going to be some particular number of hundreds. So 10 hundreds and 5 hundreds. So 10 hundreds he knows is 1,000, and 5 hundreds is that, and he gets 1,500. Finally, he adds all of the subproducts up and gets 2,072. Algamesh has come to an intermediate conclusion here. He has found that whenever you multiply some number in the tens place by the ones place, that's going to produce some particular number of tens. In this case, it was 35 tens. Now, similarly, when you multiply a number in the tens place by another number in the tens place, because each of those tens is represented by an x here, and because each of those x's, when multiplied by another x, produces 100, he knows that you can simply take these two numbers, multiply them, in this case getting 15, and then know that that tells you the number of hundreds in the subproduct. So a number of tens multiplied by a number of tens produces a number of hundreds. A number of ones multiplied by a number of tens produces some number of tens, in this case 35 tens. So that's a sub-conclusion that Algamesh is going to use to get him one step closer to our modern algorithm. What this makes Algamesh notice is that all he's doing is multiplying individual digits by one another. In this original problem, all he had to do the whole time was multiply each digit in the first number by each digit in the second number. And what that does is it gives you some subproduct that he then identifies as some number of tens or some number of hundreds to be added up later. So what Algamesh realizes is he's got to stop this repeated adding thing instead of actually multiplying. All he has to do is memorize the multiplications all the way from the digit 1 to the digit 9. He just have to memorize that set of numbers. He was probably on his way towards memorizing them anyway after all this repetition and adding over and over again. But he simply writes them down in this table that you can see here, and he's going to use this table from now on to find the subproducts. Now that Algamesh is armed with his multiplication tables, he's going to try something even harder, 45 times 324. Once again, he's going to multiply each digit of the first number by each digit of the second number. So first, it's going to be 5 times 4. Looking at his table, 20, and he's done. Next is 5 times 20. 5 times 2, which is 10, and then he's going to think about that as some particular number of tens. So this is 10 tens, which is 100. Once again, underlining the subproducts. The next subproduct is 5 times 300, or 5 times 3. Now, 5 is a certain number of ones. 300 is a certain number of hundreds, so it's going to be 5 times 3, and that's going to be a certain number of hundreds. He looks at his multiplication table. That's 15. Okay, that's 10 hundreds, which is 1,000, and 5 hundreds. This gives 1,500. That's that next subproduct. Now it's on to the 40 times different parts. 4 times 4 is 16, but that is actually 16 tens because this 4 represents a set of tens, so that is 160. He's starting to notice a pattern here. He's always, whenever it's some number of hundreds, he notices, oh, I'm adding 2 zeros. Whenever it's some number of 10, I'm adding 1 zero. He's going to keep doing the problem, but maybe this pattern is going to lead to a shortcut later. Next is 40 times 20, or 4 times 2. Looking at his multiplication table, that's 8. A certain number of tens times a certain number of tens gives a certain number of hundreds. So this is 800. Finally, 40 times 300, or just 4 times 3. Okay, but he's come across a problem here. A certain number of hundreds times a certain number of tens. What's that going to give? Well, 4 tens times 3 hundreds. What's x times c? Well, that's 1,000. So 4 times 3 is 12. He knows that. But it's 12m, 12 thousands, which is 10 sets of 1,000, which he knows looks like this. Why does it look like this? Because this is the thousands place, and if he has 10 thousands, it looks like this. He's going to call that the 10 thousands place, incidentally. And then 2,000, adding those together. So you can see this is a bit tedious, but he has now found all of his subproducts. And when he adds all of these together, at this point, the answers are not terribly interesting. We're just interested in the result, but if you want to know the answer, that's the answer. And once he finds this number, he's now written a number that's so big, the digits all kind of start to blur together. So what he decides is every time there's 3 spaces that are available, he's going to put a comma to differentiate every set of 3 spaces. So we have 1, 2, 3, comma, and then the rest. Okay, so he's going to put commas in for the same reason that mathematicians of old used to put a dot here so that 3 items didn't look exactly the same as 4 items when things start getting hairy. After all of this work, Algamesh starts to notice a pattern. For each of these subproducts, the number of zeros in the factors is equal to the number of zeros that we add to the subproduct. Let me show you what I mean. So let's take one of the early subproducts. Okay, here it is, 5 times 20. What he did is he did 5 times 2, which is 10. This is really 20 here. Since this 20 has a 0 in it, what he noticed is he simply took the 10 and added another 0 to it. Now, in like form, the same pattern appears elsewhere. Look at this. 5 times 300. Writing a 300 here in order to clarify it. 5 times 3 is 15. Then, in the final subproduct, 2 zeros are added to that 15. He's just noticing a pattern here, okay? To continue to demonstrate the pattern, I'll show you now 40 times 20, okay? So once again, he multiplies those 2 numbers by one another, getting 8, and then tacks on the 2 zeros, 1, 2, and one final time in case you're not getting it, 40 times 300, 40 and 300, which is a movie everyone should watch. That comes out to 12, and then he ends up putting 3 zeros on the end right there. 3 zeros on the end. And so he has a conjecture. Whenever some pattern emerges, doesn't prove anything on its own, but it makes it more likely that that pattern has some kind of causal reason behind it. And so Algamesh has a conjecture that maybe when he multiplies each part of each number as a subproduct, all he has to do is multiply the 2 digits together, then add zeros at the end equal to the number of zeros implicit in each of those place values added together. So Algamesh is going to try and prove this conjecture. Now, how can he do that? Well, let's consider 20 times 40 in the previous problem. Algamesh reasons that he can break this up. He can break this multiplication problem up into multiple multiplication problems. 20 is the same as 2 times 10, and 40 is the same as 4 times 10. Okay, so then what he does is he simply rearranges the problem. 2 times 4 times 10 times 10, okay? If you noticed a gap in logic here, you're right. We'll get there. But this is what Algamesh is going to do now. Algamesh doesn't know that he's just allowed to rearrange a multi-part multiplication like this. We're going to address that later, but for now, Algamesh is just going to see if this makes sense. So he's got 2 times 4 times 10 times 10. This is the same as 8 times 10 times 10. 8 times 10 can be found by adding. He actually adds 10 to itself 8 times, and that gives 80 times 10. Algamesh adds 80 to itself 10 times. He has to actually do adding during that part. You might think like, well, wait, 80 times 10 is obviously 800. Think about what Algamesh actually knows. You're going to have to hold on to what he knows from the prior videos. Try to figure that out. How does he know that 80 times 10 is equal to 800 just like that? I maintain he would have to add it up. Now, he doesn't know that that's true, but he does have an intuition that whenever he has a number multiplied by 10, all he has to do is just stack on another 0. So what Algamesh is going to do is he's going to multiply 90 times 10 and 20 times 10. He's going to add to make sure that this always comes out to what he thinks it does, which is, of course, the same number with just another 0 added. And what applies to the tens place will also apply to the hundreds place, the thousands place, etc. And so he knows whenever you multiply some number in a certain place by 10, all that does is bump it up one additional place. As a result of this, Algamesh knows he's going to have to add another row and another column to the multiplication tables in order to show what happens when you multiply a given digit by 10. He could also just remember that you add a 0, but he'll add this to the multiplication table for clarity. This leads Algamesh to the following provisional conclusion. When multiplying two numbers with Arabic numerals, multiply each of the digits of the first number by each of the digits of the second number to find a set of subproducts. Use the multiplication tables. Then add zeros to these subproducts equal to the total number of zeros in the factors of each of those subproducts. And then, of course, at the end, add all of the subproducts together. Motivation 2. So, as you hopefully remember, Algamesh noticed that he has a gap in his logic. He assumed that if you have some set of multiplications, some chain of multiplications, then you are allowed to rearrange that set however you'd like. That certainly feels intuitive, but intuition is not enough. Algamesh is going to have to prove it. Specifically, what Algamesh never proved is that if you have 3 numbers being multiplied, let's just look at the first 3, that you can switch the second and third number without changing the outcome. Now, of course, you can change these first 2 numbers without changing the outcome because these first 2 numbers, once you evaluate them, they end up producing the same number. And so once these 2 numbers are multiplied by the rest, it ends up coming out to the same thing. But Algamesh does not know if the product is affected or not when you reverse the second and third number. So this leads Algamesh to the following question. Question 2. If one multiplies 3 numbers, say 3 times 4 times 5, can one switch the second 2 numbers and still get the same result? Investigation 2. Algamesh thinks for a long time about how to prove that this is the case, and he comes up with the following way of proving it. First, he says 3 times 4 times 5 is 5 12 times. How does he know that? Well, because these 2 numbers multiply first, giving him 5 times 12. So that's 5 12 times. I'm going to underline that. Now, meanwhile, he's also going to contemplate 3 times 5 times 4 can be represented by this grid that I've just put on the screen. The top row of this grid is 3 sets of 5. Each of the columns can be taken to represent that each of these 5s are repeated 4 times. So as a result, this is a representation of 3 times 5 times 4. Since this is a grid of 3 5s by 4 5s, we know that this is 12 5s. Well, we already knew that 3 times 4 times 5 is also 12 5s, and so we can see that these two are equivalent. One can also see from this grid that this same line of reasoning applies no matter which numbers are used. So I use 3 times 4 times 5, but it doesn't matter which 3 numbers you use, the same logic applies. Algamesh is therefore able to come to the following conclusion. Conclusion 2. If 3 numbers are multiplied, the results are not altered by changing the order of the second and third factor. Motivation 3. Algamesh has realized that he hasn't yet fully proven his case. The addition of zeros rule actually requires any chain of multiplications to be fully rearrangeable. To see what I'm talking about, let's look at this 300 times 400. The way Algamesh wants to break this down is to break it down like this. He's then going to move the 4 to the front and of course get 12 followed by 3 zeros. In order to prove this kind of logic, Algamesh can make it completely bulletproof by just showing that any chain of multiplications has the same result even when you change the order of multiplication. This leads Algamesh to question 3. Is it the case that changing the order of a chain of multiplications of any quantity of numbers will not change the result? Investigation 3. Now, Algamesh already knows in the multiplication of any chain of numbers, you're allowed to switch the first two. So let me show you. So Algamesh just writes symbols to represent any number, which means he's kind of thinking algebraically a little bit. But he just says A, B, and C can be any number. Now, he already knows that switching the first two does not change the result. Why not? Well, because these two become a unit, which are then multiplied by this number. And of course, changing the order of a single multiplication of just two numbers does not change the result. Therefore, changing the first two numbers in a chain will not change the result. This comes from an earlier induction. Of course, we're just using the commutative property of multiplication. Now, what this also means, it actually means that you're allowed to switch any number of factors in the front and the factor that comes immediately after that group. So let me show you what I'm talking about. Let's say you have A times B times C times D times F, okay? What you're allowed to do is you're allowed to group these three in the front because you multiply A, B, and C and that's gonna give you a single number. And then you're allowed to switch that one single number with D. Again, you're allowed to switch any number of factors in the front with the factor that comes immediately after that. And in order to do this, Algamesh has to use these parentheses, which means treat this as one unit, as one number, which it will be once you evaluate all of that stuff. Now further, from conclusion 2, we know that we can switch the second and third factor. A times B times C is equal to A times C times B. Now finally, let's see if these three facts that we've identified so far will allow us to prove that any one factor can be moved as far back as we'd like in the chain of multiplications. So in other words, if you have A times B times C times D times F, can you move A as far back as you'd like? Well, first we can switch A and B using the first rule. Then we can switch A and C using the conclusion we made from conclusion 2 by using this rule. We've called it number 3 here, but we proved it in conclusion 2. Finally, from here, we can treat the first two numbers as a unit since they will multiply to some one number. Then use conclusion 2, equation 3, to switch A and D with one another. Again, because this becomes one factor. And that, of course, allows us to move A even further back in the chain. That same reasoning can be then used by grouping the first three together. And through this reasoning, A can be moved as far back as we'd like. So we've now proven that any factor can be moved as far back in the chain as we'd like. Now let us prove that any factor can be moved as far forward in the chain as we would like. If any one factor can be moved as far back or as far forward as we like, that means that any mix-up you want is possible while still maintaining the same product. So let's start with A times B times C times D. Okay, now if a factor is in the second place, can we move it to the first? Of course. For the reasons we've stated before, it's just commutativity. These two are a multiplication to begin with, and you can switch them without changing that product. Something can be moved from the second place to the first place. Now, can something be moved from the third place to the second place? Let's find out if that's possible. Well, yes, of course. The second and third factors can be exchanged. That's just what we came to in conclusion 2. Can the fourth position be moved to the third position? Is that possible? Why, yes, of course it is. Because these first two, once again, can be treated as a unit. then we can use conclusion 2 to switch the second and third positions. So the fourth position can be moved to the third spot. Now finally, this logic where we group however many factors we want in the beginning and simply switch the position of the next two factors using conclusion 2. This can be extended to any number of factors here on the front. Therefore, we can conclude that any factor can be moved as far forward in the chain as we'd like without affecting the result. Since you can move any factor as far forward in the chain as you'd like and any factor as far back in the chain as you'd like, what that means is that any amount of rearranging of the factors will not affect the final result. This leads Algamesh to conclusion 3. Changing the order of any number of factors of a chain of multiplications does not change the product. And so now that Algamesh has shown that you can rearrange any chain of multiplications and still get the same result, he has now proven his earlier algorithm, which was only provisional at the beginning. So let's repeat that. When multiplying two numbers with Arabic numerals, multiply each of the digits of the first number by each of the digits of the second number to find a set of subproducts. Use the multiplication tables. Then add zeros to these subproducts equal to the number of total zeros in the factors of each of those subproducts. At the end, add all of the subproducts together. Whew. Man, so you can see that multiplication actually requires a lot of work to actually airtightly prove. And it's actually really surprising. And like I said, a lot of you probably disagree with me that all of these steps are strictly necessary. After all, this probably seems obvious to you just because of the way place value works. Because it's a base 10 number system, whenever you have 10 of something in one place, it means you just add a 0 to that. Yeah, that's fine, but notice that when you do this, you're actually assuming the thing that I just proved. This feels obvious to you because the concept of place value tells you that an extra 0 is just an extra multiplication by 10. But when you say that, you're implicitly assuming that you can rearrange a chain of multiplications and get the same result. So again, this may seem obvious to you, but it all needs to be explicitly proven. And this is why I had to take great pains to prove that any chain of multiplication can be rearranged and still get the same result. Induction is not a process of generating conclusion from common sense or from intuition. It's a process of generating conclusions from that which can be known with certainty. Certainty can only come from direct observations and reasoning steps from prior knowledge which themselves have been validated by a chain of reasoning which originates in sense experience. That is the point of going in order so that we can go all the way from direct observation to each of these higher abstractions in turn. That is why these inductive videos are going in order without skipping anything. So if you'd like to continue to join me on that inductive journey, join me next week as Algamesh reinvents our modern long division algorithm. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series, An Inductive Summary of Physics. I'll see you in the next video as this inductive journey continues.